trying to get the microphone, but before that I can give you some quick overview. So my name is Tomasz, and I will be here for a week, and we will do some I hope interesting stuff. I'm involved in the programming competition for 12 years. I was in the ACMI CPC World Finals in 2005 in Shanghai, and from now mostly I'm involved in preparing the competition back in Poland. So I'm mostly preparing the tasks for the various competitions we have, like for the national programming competition or the algorithm engagements. So and also for competition for high school students. Some of the tasks from these competitions we'll be doing at this camp. So what is the plan? So we will have 5 lectures and 5 competitions. So the lectures will be in the mornings and the competitions in the afternoons. We will have 3 team competitions and 2 individual competitions. And in the lectures we will be mainly talking about the solutions from the previous competitions. This day will be an obvious exception because we didn't have a competition before, so we will be just talking about. Okay, we will see. And okay, so for the competitions, the tasks are supposed to be challenging. So don't get discouraged. And the main thing is perhaps you won't solve everything during the contest. So, but you are not supposed to, because they will be quite hard tasks. But then later in the lecture we will be talking about solutions. So you get the idea, and I really encourage you to solve them afterwards. So and the system will be, after the contest, there will be also a possibility to solve the problems, and I really encourage you to solve them, and to because okay, one thing is to know the algorithm, to know the solution in theory, but to actually correctly implementing the solution, it's the second thing. And it's not, and usually it's also challenging to actually implement things, because when you are implementing, many additional things which were not very clear or you didn't see them during the lecture will come up. So you will have some additional details, implementing details you will have to consider. So I really encourage you to try to implement the solutions. Okay, so at the lectures we mainly be talking about the algorithm stuff, but sometimes we also mention something about the implementation, how to implement things maybe faster, maybe in a clearer way, and we'll be mostly using C++. And so one thing about implementation, you can. I think there's many materials on the internet how to solve the problems from the algorithmic perspective, how to get the right algorithm. But also there are sources when you can learn the implementation. For instance, in Topcoder, the source codes of the contestants are available, so you can just see the source codes of the best Topcoders and try to read the source codes and try to learn from them, because in many times you will learn some new tricks just by reading the codes of other guys, and this is really I think it's really important, but usually it's not it's not stressed much because mostly we are focusing on the algorithm part, but I think the implementation part is also really really important. Okay, so that would be for the quick introduction, and now we can we have the microphone. Hello, do you hear me? Yes. Okay. One again. 1, 2, 3. 1, 2, 3. One, two, three. 1, 2, 3. No? So we need this microphone to get the. I hear myself. Because we like to have the clear voice to the camera. Okay. Okay, do you hear me? So let's start. So on today's lecture, we will be talking mainly about dynamic programming. So dynamic programming is one of the various programming techniques you will have to know to perform well in the competitions. And there are many different tasks which can be solved using dynamic programming, and you probably know some or many of them. So what are the examples of the tasks you can examples of problems of which you can solve using dynamic programming? Okay, that's the easy question. I'm just checking whether everybody is asleep or. Sorry? Oh, what do you mean counting?
For counting how many ways we count.
Okay, so counting things like combinatorial things. Yes. What was that? Okay, combinatorial. What's the name? What's like the most standard example of using the dynamic programming? Maps. Okay. And maybe something easier. What's good? Point change. Okay. Okay, Fibonacci. Sorry. So let's start with Fibonacci because this is a very simple example. So how do you? So the task is to calculate the nth Fibonacci number. So Fibonacci numbers are given by the recursion. So the first Fibonacci numbers are just ones. And to calculate the nth Fibonacci number, you just sum two smaller Fibonacci numbers. So this is the clear example that we want to calculate some object, and for calculating this object we need to the object of smaller sizes. So, for instance, to calculate the nth Fibonacci number, we use the Fibonacci number which are small. So, usually, when you want to apply dynamic programming, you need to first find this recursive formula, which somehow combines the objects of smaller sizes into the solution of the bigger size. And the Fibonacci is a very good example because it's clearly in the definition you have this recursive formula. Okay, so how do you do this? So first of all, you can if you think about the dynamic programming, there are two ways to try to implement it: the top down and bottom up, and they are also called like recursive with memorization or simply dynamic programming. So the easiest way is to do the recursion. So for instance, if we want to we can write a function which takes the argument which is the number of Fibonacci number we want to calculate, and we just in this function we can just rewrite in the programming language this recursion. So first of all, we need some we need to include the border cases. So for if n is less or equal to 1, we just return 1, and if not, we can just recursively invoke this function. Okay, so that code will be correct. Why it's not good?
Because you're calculating the same number many times.
Yes. So the time complexity of this implementation is very poor. It's in fact exponential because to calculate the number n, we need to mostly calculate two other numbers. So we get and again we get an exponential growth. But if we want to calculate the nth number, we will only need at most n smaller numbers. Yes, so it's not this exponential growth is not immediate. So what we usually do, we just have to somewhere memorize all the previous solutions. So we need some caching. So now can we do this? We can just write a map which will store the previously completed solution for us. And yeah. So we can leave this case because it does not involve recursion, so it will be fast. And if we find our n in the cache, we just return it. And otherwise, we are calculating it for the first time, so we just can write So we just calculate it, we put it in our cache, and we are returning the calculated value. So okay, so now we only calculate, every number is calculating only once. So the time complexity of the solution will be polynomial. The slight problem is that if we are using the map will give us the log n overhead for the caching. So this algorithm is then it's n log n, but we can use for instance, the hash map to make it to the optimal. Okay, so this is recursion with normalization, but we can do real dynamic programming, and we can go from bottom to top. So in dynamic programming, we just fill the table, fill the array in which we will store all our values. So, for instance, we can get an array D of size capital N, which will mean the biggest size we need. So we just write the border cases in the table. And then we just go with the loop. And with the loop, we will calculate all the values using the previous one. So what is the what is the time complexity of this solution? It's clearly O of n. Okay, so I'll be using this microphone. So the time complexity of this solution is clearly linear. And what are the advantages and disadvantages of this approach and of this approach? So this one is usually faster if you want to. So if we are on the competition and we are solving some dynamic programming task, so usually we start with writing this recursive formula for the task, and then it's easier for us to write a quick solution just by using the normalization, because it's like usually one-on-one correspondence between this recursive formula and this code. But what are the disadvantages of this thing? Well, first of all, it depends on which data structure we use. Here, we can get a little time overhead of using the cache. The second thing, we can get a little time overhead of using the recursion to actually invoke the calls. If we have the deep, if the number n is large, we can get a deep recursion, and then we can have the problems if the stack limit is smaller. We will get to this, and I think in the later lecture. So we can also have some problems here. So overall, this approach is better if you want to make the fast call. Well, there is one exception when this could be faster is when the space state is not fully exhausted. So in this case, we use all the values in this array. So this actually will be faster. But if this array if we will not use all the values, and we are not sure which values we will be using and not, this approach would be faster because it calculates only these values that are essential to the solution. And this approach calculates all the possible values. And also in this approach, we must be careful about in which order we are calculating the values. So if we are calculating the n, we must be sure that all the smaller values we use are already calculated. Okay, and there are other advantage of this solution. So in this solution, we are not controlling in which order the cache is filled. So we just put all the values here, and the cache will just carry all of them. But in this solution, we control it. So for instance, if some values are not really needed, we can just free them, and then we can use less memory than we actually than in this solution. So for instance, if we don't want to calculate all the Fibonacci numbers, and we are interested only in the last Fibonacci numbers, so we don't have to store all this array. Yes, because now on time it's time complexity, and the memory complexity is all n. But we actually can make this code to have the memory complexity of all 1. Yes, because if we calculate the nth number, we only use two last numbers. So everything we need to remember is to remember the values of the last 2 numbers, and then this memory can get to the constant count. So in this case, it's not a big deal. But if we are solving the tasks when the array is in quadratic size, we usually have time to calculate something in quadratic time, but we don't have so much memory to actually store the quadratic array in the memory, and then we can use this technique to see which rows of the array are not needed, and then we just discard. Okay, so let's take a look at another classic. Another classical dynamic programming task is to find the longest common subsequence. Okay, so we are starting from the basic, but we will gradually go to the more advanced material. Don't worry. So the thing is, we have 2 words. One word of length n and another word of length m. And we want to calculate the longest common subsequence of these words. So in other words, we want to erase some letters from the first word and some letters from the second word in such a way that the letters which will stay will form the same word here and the same word here. And we want to calculate what is the longest word we can get. So here the recursion is also, I think all of you will know this recursion is as follows. So we are we are looking at the prefix of the first word and at the prefix of the second word. And let's say that they are ending on the letter I and the letter J. So the first prefix is of length I and the second prefix is of length J. And by Dij, we mean the longest common subsequence, which is enclosed in this prefix and this prefix. So what is the recursion? So we have two cases. Either the last letter is the same, and then we just take the longest common subscript of shorter prefixes, or the two letters are different, and then only one of them can go to the longest common subsequence, and we just need to take a maximum of these vowels. Okay. So again, we can fill the array, and clearly the time complexity of this solution will be, let's say, n times m, and the space complexity will be also n times m if we just store the whole array in the memory. But the thing is, we do not have to store the whole array, because what information we need to actually fill the cell which is in the ith row and the jth column. So from this recursive formula, we see that in the first case we only need this this guy, and from this formula we see that we only need these guys. So actually, when we are filling this array, we usually fill the array by row. So we just write the loop which is going through I, and then the loop goes to J. So we only needed the last two rows. Yes. So if we are filling the row I, we need only the information from the row I and from the previous row. So these rows can be discarded. So actually, what we can do, we just store in the memory only two rows, and then our memory complexity will be all of them. Okay, and sometimes we don't have much memory to store the whole array, then we will have to use this trick. So okay, so in dynamic programming there are usually various loops which are asked to calculate. The one thing is to calculate the size of optimal solution. So in this case, we are just calculating the length of the longest common subsequence, not the common subsequence itself. But sometimes we are asked to actually calculate one of the solution. So some solution of optimal size. And this is a little bit trickier, because usually first we fill this array, and then we use this array to get this sample solution. We'll talk about this in a moment. But there are different things which can be asked for. For instance, we can ask for a solution with some property. So for instance, we can be asked if our multiple longest common subsequence, we need to calculate the common subsequence which is the, for instance, lexicographical smallest. So it's this another thing. It makes our solution a little bit more complex. So let's take a look at this one, and let's try to calculate the sample solution. So if we have the whole array, so we probably know that so if we are in this cell, so we were using for I and j, we were using this part of the recursive formula. So we were coming from this cell, or either we were using this formula, so we were coming from this cell or from this one. So we can actually store in this cell not only the length of the longest common subsequence, but also the place, the cell which we are coming from. And then if in the last cell, so in the n-1, we have the answer to the lowest to the common subsequence, but also we have this arrow which says from which cell we come to here. Okay, so we can, if we have for every cell this arrow, we will just calculate the path to the first cell, and using this path we can write down the longest common subsequence. The longest common subsequence will have all the letters which are denoted by this diagonal arrow. Okay, but to actually get all these arrows, we need this whole array, whole quadratic array. So the question is, can we do this using only linear memory? So we see that we can calculate the size of this optimal solution using linear memory, but can we use this calculate the sample solution using linear memory? And the answer is yes, but it's quite tricky. So the trick is as follows. So the sample optimal solution will use some path through the array, and we will use divide and compare method to partition our problem into two smaller subproblems. So let's take the middle row of this array. So this would be a row and a half. And let's assume that someone gives us the information that which cell in the middle row contains is the cell which lies on some of the path of the optimal solution. So let's assume that this is this cell. So what can we do? So we know that if this cell contains optimal solution, then the solution on the from the lower rows will be contained in this rectangle, and the solution from the upper rows will be contained in this rectangle. And we just calculate the solution recursively for both of these smaller rectangles. And then we do this again recursively. So let's see what is the time complexity of this of the solution, because now we are doing much more work, and we still want to have this quadratic complexity. But as you can see, the size of these two rectangles is the half of the size of the whole rectangle. So that actually, if we look at the so the time to calculate the first rectangle is m. The time to calculate the smaller rectangles will be m times m by 2. And again, recursively, the time to calculate for the smallest rectangle here, if we are given the position in the middle row, will be again divided by 2. So which is m times m by 4, and again. So if we sum it up, it equals n times m. So it's at most two times slower, but the overall time complexity is the same. Are you still with me? Okay. So what do we need now? We just need this cell to be known. Yes, because we assume that somebody told us which cell the optimal solution will traverse through, and it's not the case that it doesn't have to be like the middle cell. Yeah, the optimal solution could just go through. It can go like this, or it can go like this, and we don't know. So there are at least two possibilities how to calculate this. The one possibility is to first calculate the length of the optimal solution for the first half. So we store here. We just remember the row, the values of t in this row, and then we calculate the optimal length starting from the back. So we're calculating it for these rows by just reversing the order of the words. So we just calculating. So here we calculate what are the optimal paths from this node, and here we calculate what are the optimal paths from this node. And so when the cell contains can contain an optimal solution, so we can before that we can calculate the d and m. Minus m minus 1 and minus 1, so the optimal solution of the whole world. And then if some cell is in the optimal solution, the the sum of this part and the sum of this part must be equal to this number. So if we have the optimal solutions for the top part, and if we have the optimal solutions for the lower part, we just take in the sum, and if the sum is equal to the length of the longest common sequence of both words, then this cell is the part of the optimal solution. Okay, so that would be that. So here we have that, like, calculating the sample solution is a little bit trickier if we want to have small memory. And calculating the solution with some property can be even more tricky. So for instance, I don't know how to do that, how to do this trick when we, for instance, ask for the longest common subsequence, or which is the lexicographical smallest. So it can be a challenge for you to think of that, how to do this with small memory and to get the longest common subsequence, which is lexicographic smallest. So usually in the contest we will have either we have to calculate the size of the optimal solution or the sample solution. But there are also, we can be asked about the number of solutions. And number of all solutions, of number of optimal solutions, and usually this number can be quite big. So I think most of the contests, if we are dealing with if we have to deal with big numbers, then we are just told that we have to calculate the Sphinx modulo some number, just to not cover the interesting part of the algorithm by implementing the big numbers. Yeah, so that would be it. Let me see how much time. Let's pick up 1 hour. Okay. So another thing which is important in dynamic programming is the space state. So actually, what states we need in order to get to our solution. So for instance, in the longest common subsequence, we have 2 words, and the state was comprised of 2 numbers, and these 2 numbers means the length of the 2 prefixes. So we can, so basically we have like 2 objects which are lines, and then our state is just 2 prefixes. So we can, of course, have 1 prefix, and it's also common. So we have an array, and our state is just the length of the prefix. And if we want to calculate some value here, this value is only the value here which only uses the calculations from the values in the prefix. So one of the most obvious applications of this is calculating the prefix sums. So, for instance, if we have the array, and we need to answer many queries, which are just, each query consists of the infix of the array, and we are from I to j, and we are asked about what is the sum of all the numbers in this index. So we could do this naively, like just summing every number in this index, and it would give us linear time to answer the query. But of course, we can do better. We can get to the constant time for a query by using prefix sums. So it's easy to see that if we are just using the addition, so our operation can be reversed. So to take a sum of all numbers in the infix is just the sum of all numbers in the one prefix minus the sum of all numbers in another prefix. So let's assume that we have, well, maybe let's not assume, just calculate. So we want to calculate the array which will store all the prefix sums. So it's convenient to make also the prefix of the empty, the sum of the empty prefix will be 0, and the sum of the prefix I will be the sum of the prefix I minus 1 plus the additional number. So this time it will be I minus 1 for I from 1 to n. So if we have these prefixes, and we can calculate them, of course, in linear time, so we can just do the preprocessing in the linear time, then we can answer our queries. The answer is just, so the answer for the prefix from I to j, and now we need to have our pieces right, so that would be a prefix from j plus 1 minus prefix of I. Yes? I think so. Okay, so now we have all the queries in the constant time. One thing to which we have to maybe which is sometimes dangerous to see, it's the indices. So we can start like indexing our arrays from 0 or from 1, but we need to be like consistent, or we need to remember which arrays are indexed from 0 or from 1. So for instance, I like to index all of my arrays from 0, but then I will get into some inconsistency here, because for instance this array is of length n, but the prefix array is of length n plus 1, because we need to take care about this prefix of size 0, and then we have to be careful in this indices, where should I put +1, where should I put minus 1. So these are things which you should be careful about, because it's easy to just put +1 in one place. And also there's a thing about if we have a range. So for instance, this query was from I to j, from I to j inclusive. So usually it's so there are two schools of getting these ranges. Either we have the range which is inclusive, or we have the range which is inclusive on the left side and it's exclusive on the right side. So this would be j plus 1 and it's exclusive. So for instance, if you are using STL, so I think you know this kind of ranges because they are using in STL. So if you have two iterators which are talking about one range, then the first iterator, the begin, is inclusive, and the end iterator is excluded. So it points to not to the last element of the range, but to the element before the last element. So this has some advantages. For instance, if we have an array and we want to talk about this range, so here we have the in and here we have n. So n is after the first element. So for instance, it's easy to talk about the ranges of which are empty. So the range which is empty is just the begin is in the same place as n. So these are the same. In this, if you would go for this ranges, then the empty range will have the j will have to be smaller than I, and it's not. It's kind of confusing. And another thing which is nice about this kind of ranges is if we have two ranges which are next to each other. So we have one range and we have another range. So let's think about this will be I, this will be j, and so this will be k. Or if we want to just have the one range and we want to split it into two halves, then this index k will tell us the end of the first part and also the beginning of the second part. So then the range ij is just the range ik is range. So we do not have here like plus ones, minus ones. So especially if k is some kind of involved iterator, you don't have to like increment it or decrement it to talk about two parts. So as I said, it's heavily used in STL, and I think it's good to know it and to adapt it to your style of programming. Okay, so these are prefix sums. These are one-dimensional prefix sums. We also can use the two-dimensional prefix sums, which are also useful. So for instance, let's generalize this problem. So let's assume that we have an array, and the queries are where you have some numbers in the array, and the queries are in the form what is the sum in some of the rectangles. So we are giving the rectangle using some and we want to just sum all the numbers in the rectangle. So again, we can do this naively by just summing all the numbers, but we can use also the prefix sums. And so let's say that this rectangle is given to us by the this kind of range. So it's A, B in one dimension. Let's see, B in this range. Once again, this kind of ranges are usually used in the problem statements because these are more natural if you just formulate the thing in not technical way. Yes, so you have to if you use these ranges in the implementation part, you just have to be able to easily transfer these two representations. Okay, so we want to calculate sum of all the numbers in this rectangle. So how can we do that? So let's generalize this. So if we want to calculate all these numbers, we can firstly take this whole prefix. So again, we will talk about prefixes, and two-dimensional prefix can be seen as if we have the one cell. These are all the cells which are above and to the left. So let's say that this will be the answer for this thing is just a prefix from B to B. So we summed all these numbers, and we want to get rid of some numbers. So, for instance, we want to get rid of all these guys. Yes? So let's take another prefix. So let's take this one. So we just want to subtract all the numbers which are in prefix B and C minus 1. Okay, so now we have to get rid of these guys. So we have to subtract that you see I minus 1 to D. And we are almost done. Yes, but let's take a look at these guys here. So we subtracted them 2 times. So we have to add them once again. So we just add the prefix from A minus 1 to C minus 1. So if you are familiar with the inclusion-exclusion principle, this is the simple application of it. Yes, we just sum all the numbers, then we just subtract these guys, and we have these guys which were subtracted twice. So we have to add them once more. Okay, so we can answer our queries in the constant time using this prefixes, but the thing is we have to calculate this prefix array. And how to do this? Well, by using dynamic programming. Yes, we can, and actually we can use the very same technique, because if we want to calculate this prefix, we can assume that we have calculated all the prefixes which have smaller indices. So, for instance, we calculated this prefix. So we can add all these numbers here. So it's prefix I j minus 1. So now we only have to add all these numbers. So there are linear of them. So we can just add them one by one, or we can make another array which will, by using dynamic programming, which will calculate all these columns for us. But actually, we can use only the prefix table. And the thing is, we can use the very same idea. We just add all these numbers again. So we now using the second prefix. So this prefix is I minus 1 to j. And now we have all these numbers added twice. So we have to subtract them once, and we just using the prefix I minus 1, j minus 1. So we subtracting. Okay. So this recursive formula will allow us to calculate the prefix table in time and times n. And then we can answer these queries in the constant time. And it's easy to see that this idea extends itself for the bigger dimensions. So if you want to, if we have like some kind of cube and we want to calculate all the sums in the subcubes, we can just use this idea. The formulas which will be slightly more involved. Here we have two terms to add. Here we have 4 terms. For 3 dimension, it will be just 8 terms. Again, using the inclusion-exclusion principle. Okay. So that was the prefix sums. So again, the space state was just a prefix. Another example of the space state is an infix. So, okay. So we have again, you have some array, and then we want to calculate some values for every infix of the array. So for every range. And so one of the example of the task which will involve this is as follows. We are getting a word consisting of some English letters, and we want to form a palindrome of this word. And we are allowed to insert some letters in the places we would like to insert. So, for instance, if we have a palindrome is a word which is read the same forwards and backwards. So, for instance, if we have a word so to form a palindrome, we can, for instance, insert A here, insert B here, and insert D here. So in this case, this word would spell out A, B, A, B, B, A, B, here. So it's the same from left to right as from right to left. So we are asking what is the smallest number of letters we have to add to this word so that this word will be a palindrome. Okay, so let's take a look at the whole word. So we have actually, if you have a word, there are two possibilities. If this word have to be a palindrome, the first letter and the last letter of the word must be exactly the same. So either these letters are the same or not. So let's take a look. So for instance, we have some word, and the first letter and the last letter is the same. So how we can construct a palindrome? Well, the thing that these letters are the same is okay for us, and we can just forget for a while about these letters, and then just calculate the optimal solution to the smaller word. So if we make a palindrome of this word, so if we can get a palindrome here, then we just can add these two letters, and then we have a longer palindrome. So if these two letters are the same, then the optimal thing to do is just to calculate the shortest way to do a palindrome from the rest of the word. And so this is the first case, and the second case is when these two letters are different. And what to do then? So now either we have to add some A to the palindrome, or we have to add a B in some place. So we have to decide which letter will be the first and the last letter of the palindrome. And if it's A, then we have to add A. So we add another A, and then we have to form a palindrome from the shorter word. And if we add B, so we add B at the beginning, and then we have to form a palindrome from the shorter word. Okay, so what is our space state here? So the space state is just an infix, yes, because in this case we are shortening the word from by one letter from the left and by one letter from the right. Here we're shortening by one letter from the left, here by one letter from the right. So we can write our recursion formula. So we just, for the Dij, it will be the shortest way to get a palindrome from the infix A, J to A1. So what is the formula? So if two letters are the same, then we just have to make the palindrome from the shortest word. I plus 1, J minus 1. And if they are different, then we have to consider two possibilities. Either we add, first of all, we have to add one letter, so we have 1 plus, and the number of letters to add in the shorter word. And this is I minus 1 J. or we have 1 plus and the other one. So this is okay, so this is for the infix. So usually in the dynamic programming we will have not only this two the state can get equal. For instance, for each infix we will have to store some additional information, and we will see this kind of problems in the I think in the next lecture. Okay. So, what are other objects on which we can do some dynamic programming? So, up to this point, we are talking about arrays. We are talking about 2 arrays or 2-dimensional arrays. We also can talk about trees. And for the rest of this lecture, we will talk about dynamic programming on trees. So usually when we talk about dynamic programming on trees, we will talk about rooted trees. So each tree will have a root and some nodes below. And the tree do not have to be binary, it can be just an arbitrary tree. In this case, the main thing in the state would be the node of the tree. So, for instance, we have the node of tree B here. It's a root, and so we want to calculate some value for the root. So the value for the whole tree, and by doing it, we will use the values which are calculated for the children of this root. So here we have children U1, U2, U3. So we can have some kind of function which will take the values of U1. So let's call it like that. Up to so what is the simplest example for this kind of dynamic programming? We can be interested, for instance, in the height of the tree. So the height, which is, in other words, the longest path from the root to some of the leaf in the tree. So, for instance, here the path consists of 1, 2, 3. The longest path consists of three edges. And what is the recursive formula for height? So P of P equals 0 if V is a leaf. So our border case here is usually when V, if the node is the leaf of the tree. So then for every leaf, the height of this tree is 0. So what if V is not a leaf? So the height of the whole tree is just 1 plus the maximum heights of the subtrees in the children of the children group 1 to 11. So it's just 1 plus maximum from the 1 to the 11. And then we can use, it's easy to use recursive with memoization with trees. But then again, we will have to look for the size of the stack. If the size of the stack is not very big and the tree is very tall, so for instance, for many tasks with the trees, we will go from the OOM solutions. So the linear solution in terms of the number of nodes in the tree. And if tree is very tall, so it's only one path down of length end, it's easy to, so then the recursion is also of height n. And if we do not really control how much memory the compiler needs for the recursion, so it can get really big, and if the stack is not verified by the, so then we could get in trouble. So another way to do this is to do the dynamic programming, and then what we need is beforehand we need to calculate the ordering of the nodes, and here we need the ordering starting from the leaves and going to the top. So we just first of all we need to preprocess this tree to get the correct ordering of nodes, and then we can just apply this formula in the loop. Okay, so what is the? So let's take some more tricky thing with trees. Okay, so let's talk about maximum independent set in the tree. Okay, so we have a tree and we want to select some of nodes of the tree in such a way that if we have an edge, at most one node is selected from this edge. So, and we want to select as many nodes in the tree as possible. So, for instance, if we select the root, so we cannot select both of the children of this root, so we can select this guy. We can select this one, but we see that it's better to select these guys. We can again select this one, and so if we select this one, we cannot select those. But so this is obviously not the maximal independent set. We can do better, but just to give the picture. So maximal independent set in the Java way, it's a hard problem. But for trees, it's kind of easy. So we can do dynamic programming here. So let's try figure out the dynamic formula for this problem. So when D is a leaf, so what is the maximal independent set for the leaf? It's 1, because we can take just a leaf. Okay, so let's now figure out what to do when we have the root and we have some subtrees. So it's always convenient to write this way. So we have the root and we have some subtrees. And for subtrees, we have already calculated all the information we need. Okay, so we are just wondering, can we just see what is the maximal independent set in the whole tree based on the sizes of the maximal independent sets in the subtrees? So how can we do that? So this is the first question. And the second question which we can be asking ourselves in parallel is how does this vertex be? How does the root is involved in the solution? So for instance, if we are asking ourselves about the independent set, so the question is whether this vertex will be in the set or not. So let's assume that this the vertex B is not in the independent set. So then, so what is the largest independent set in which vertex B is not covered? Yes, it's just the sum of maximal independent set in all of the children. So we can write D equals just sum over D, right? If D is not taken. Okay, so this is the one case. And another case is, what if we take the vertex V to be in the set? So what then? Sorry? Yes. So in this case, we get some restrictions on the form of the set. So we get some restrictions for these subtrees. So if we take the root, then we cannot take the roots of these subtrees. So it turns out that the size of the maximal sets in the subtrees is too little information for us. We need some more information, and here we need information about what is the size of the maximal set in the subtree if we do not take the root. So let's call it D. For instance, let's call it dt. If D, so dn will be not taken, and dt will be taken. So instead of one array D, we will have two arrays. It will hold the information about the size of maximal independent set when the root is not taken and when the root is taken. So for instance, here we just calculated the case when the root is not taken, and yeah. So what about if the root is? So what about if the root is taken? So first of all, we increase our sorry.
On the sum, you have to change the formula to match between dt and d.
Yes, we will come to this. So for this part, we'll have to plus get 1 to include the vertex v in the solution. And then we just take the sum of all the sizes when the roots of the subtrees are not taken. So here we have the n. Okay, and so this looks good, and we have to think a little bit about this formula, because here we have d, and we no longer have d in array d. So if v is not taken, we have no restrictions about whether the roots of the subtrees must be taken or not. So we just take the maximum of the two possibilities. So we just take max from the Vn and Vt. Okay, so this is the case when we are not the leaf, and we also have to finish the case when V is a leaf. So if the leaf is not taken, then it's just 0 because we cannot take it, and if the root is taken, then it's just 1. So that's the solution. So one thing we can see here that we really don't need two separate cases here, because if we see the formula for if V is not a leaf, if V is leaf, and we see the formula here, so it does not have any children. So this sum will be 0, and the sum also will be 0. So these two formulas will coincide if V is a leaf. Okay, so we got an odd solution for this problem. Actually, we do not have to use dynamic programming for this problem, because it's easy to see that we can come up with the greedy solution. And the greedy solution is just select all possible nodes from the leaves, starting from the leaves. And so we can just select all the leaves, and we look at whether we can select this one or not, and if not, then do not. And if we can select some vertices, for instance, if we can select the root, and we can select it. And it's easy to see that this solution is correct, because if we, for instance, if we do not select some of the lower nodes, and if we could select them, we can just take the selected node from top and just put it down. So if we do, so if we say that in some optimal solution we would have to select this guy and not these guys, so we can just push it down here, and to get the solution which is at least the same size. So we can go here with the greedy solution, but only in the case when we are talking about the size of the maximum independent set. But we can make this problem a little bit harder and talk about the maximal independent set of maximum weight. So, for instance, if each node has additional weight, and we want to select independent set which the sum of the weights of the selected node is as much as possible, then the greedy solution will not work. But our dynamic programming solution will easily work. Because here we do not add 1, but here we just add the weight of the root. So it's an easy change, and we get a more solution to the more general problem. Okay, and this also shows us a little bit more involved state. So in the state we have, first of all, the vertex, and then the flag whether the vertex was taken or not. So it's a matter of taste whether we want to have the two separate tables, two separate arrays for this, or whether we can go with one array DB, which also has the flag whether it's taken or not. So here we will have like 0 or 1. So we can use both. Okay, so maybe one more interesting example from the trees. Okay, the question will be as follows. We have a tree, and we want to visit all the nodes in the tree, but we can go only from one node to another node, but we couldn't jump very far. So let me just write an example. Okay, so here we have a tree, and we want to find a permutation of the nodes in such a way that if we are going from one node to another node, we can jump at most. We can go at most for 3. So for instance, from 6 we can go to 5, we can go to 4, and we can go to 2, but we couldn't go any further. So for instance, so what would be a solution for this tree? Well, we can start in any vertex we want. So I think it's not absolutely obvious how to do this. So let me just. Okay, that's supposed to be one of the answers, and let's take a look whether it is correct. Okay, so we go from the node 7 to node 2, jumping by 2. Then we go to 3, jumping 1. Then we go to 5, jumping 1 to 3. So it's at most as we can get. Then we go to 6, jumping by 1. We go back to 4, jumping by 2. And we go back to 1, jumping by 2 again. Okay, so we can jump almost 3. Okay, so the question is, we are given the tree, and we are interested in this permutation. So at first sight, it's not very obvious whether for each tree such a permutation exists. The answer is yes, it exists. But how to, first of all, how to prove it, and then how to make an algorithm for this. So usually, if you want to prove such a thing, then the right order is to just write an algorithm, and the algorithm is just a constructive proof that this works. Okay, so how to come up with an algorithm? So again, we will use dynamic programming, and so I like to, if I want to use the dynamic programming trees, I usually write this kind of picture to see what is the recursive formula for it. So let's take some root, and let's take some subtrees. Okay, so it's not very clear if we are looking at the whole tree, what would be the ordering of the traversal. But we can assume that. So suppose that these are big trees, big subtrees, yes, and we can just make jumps of length 3. So it's not possible, like, for jumping from this part directly to, for instance, this part. Yes, because if here you have big height, so it would be too long for us. So these jumps shows us that they are mostly. So we can just start from the top of the tree, and then we can cut to some other trees. So these jumps won't be possible. So that gives us some intuition that probably the dynamic programming will be can be used, and we can make some. If we want to visit all the tree, then we will have to make some recursive visits first for the first subtree, for the second subtree, and again. We still don't know in which order, but we know that if we go here, then we will have to visit all this tree before we go up. Okay. So let's try to do this. So let's suppose that we are starting from the root, and the first jump is to the root of this subtree. So then again we have to go through all the subtree, and then we will end up in some other node of this tree. So which node should it be? Well, if then we want to jump to the second subtree, we will need to make the jump of length 1, 2, and then at most 3. So we have to end our trip in this subtree in the child of the root. So let's assume that we are starting in the root. We make a traversal of this tree using the jump at most 3, and we are ending up in some child of this root. So then, if we have this, then we can make the jump of 3, 1 to 3, to go to this root. Yes, and again we can make it recursively, finishing in the child of the root, and then go to this root, and then finishing in the child of this root, and then what? So we can say, okay, we visited all the tree, but it's not enough, because we are saying that, okay, we know how to traverse these smaller subtrees in a recursive way. So we made some assumption. We made that assumption that we are starting in the root and finishing in the child. And we want to have this assumption also for the bigger tree. Yes, if we want to make a recursion. So, but in the bigger tree, we started in the root, we go through the tree, and then we finished in this node. So every node is already visible, so this node is a grandchild of the root and not a child. So what can we do about this? Because the thing is, we are almost ready with the solution, but it's only one additional remark. Backwards. I heard backwards, yes.
You start by going there and then do it backwards.
So let me see, what have we done here? We have a tree which goes from here to this node and finishes here. But our edges are bidirectional. Yes, we can go through. If we go backwards, we will have also the valid tree through the tree. So the thing is, we can start from not from this node, but from the last node of our tree. So we can go jump from 1 and 2. So we can jump here, and then we can go backwards. So every edge every path should be reversed. And then we are just finishing in this node. And this node is the child of the root. So it's good for us. So we have this recursive scheme. So essentially in our so here we do not even have to like fill some kind of table for dynamic programming. We just write the recursive we can just write the recursive formula, and for the recursive formula we will need not to know two values. First of all, the number of the node of the root, and then one flag which will tell us whether we go forward through all the tree or whether we go backwards. So if we write the recursive formula for V and we have some flag, then we will have to invoke recursively for all the children, and this flag will be just 1 minus flag. So if we do 0, then it will have to be 1. And depending on whether this flag is 1 or not, we are just writing out this root either on the beginning of the recursive or at the end. Okay, so it's 11:30. So I think we will stop here. So this afternoon we will have the team competition, the password, to get a password for the competition arena. You will have to register them. The link is in the email list. And good luck and have fun.